Good afternoon, class. Let's begin. Today, what I'd like to do is finish up what we've been talking about in the last few classes. And one way to summarize, or at least just put a title on what we've been talking about the last few classes, and that's electrostatics. So anytime in your whole life you've said, static, like static electricity, we often use the term static to be short for static electricity. What that means is just electricity that's static. It's not going anywhere. It's not moving. There's some fun examples of that. I think lightning is a fun example of that. But really, most of our life is enabled by electricity that's not static. And so usually the term electricity, when people say electricity, they mean that type of electricity that's moving. And so spend a couple more minutes today talking about a couple things we didn't get to last class. And then we can start getting the electricity moving. I think that's the fun part. So today will be the last day I have my Van de Graaff machine. So if you really want to see your hair or your friend's hair stand up, today's the day. I might even try to wrap up like 3 minutes early to have some time for playing around with the Van de Graaff machine. So back to the Van de Graaff machine just briefly. As we've discussed, the Van de Graaff machine is a very good example of lightning and Van de Graaff machine are both examples of the same phenomenon. And that phenomenon is charge separation by rubbing, triboelectrification, charge separation by rubbing. So I've got a nice little setup here, not too complicated, just two belts, a belt and two pulleys, and a nice little dome up here. And inside, as we've talked about, the important component that is not visible is those little combs. And so we'll talk a little bit more today about why those combs are so important. But I've got a couple pulleys and a belt, and I can get a very large amount of charge distributed on the top of that dome. And I believe the way this works, so Van de Graaff machines are different. I believe some Van de Graaff machines yank a bunch of extra electrons off the dome and leave it very positively charged. Some Van de Graaff machines are the opposite. They dump a bunch of electrons onto the dome and they leave it very negatively charged. Either way, you get a cool effect. You get to play around with it, you get lightning, stuff like that. Okay, so this is a good example of that. We'll talk again about lightning. Let's just really quick review. So this is my person with lots of hair on their head. And so what's going on is that whole system is electrically charged. Let's say that's negative. So what the belt has done is just yanked electrons, probably deposited electrons. So just dumped tons and tons of extra electrons onto that metal ball, and that metal ball is also probably conducting some of those electrons up into the pom-pom. Now those pom-pom leaves or feathers, whatever you call those bits, are all charged. And there she is. Like charges repel. Like charges repel. So I've got a bunch of like charges, and that's what goes on your hair. You've got a bunch of negatively charged hair. It wants to run away from all the other negatively charged hair, and it arranges itself in a way to get as far away from itself as it can. And in the absence of gravity, it would be a nice, perfect pom-pom shape. Gravity's kind of going to pull it down a little bit. Now, one thing I've mentioned a couple times it's important to the functioning of that thing is those little combs. So what goes on in those little combs is those combs receive some voltage. And those combs are, some pretty high voltage. Now, when I've got a nice round, smooth dome like that, I can generate a lot of voltage before I get a discharge. Now, you guys can hear the occasional discharge. So as that dumps electrons and more electrons and more electrons, it eventually reaches a point where it's maxed out. You can't get any more electrons on there. The field gets so strong, it ionizes the air, and it jumps into the air and creates lightning. That's what you're hearing. You're hearing the thunder that's a result of the lightning. That was awesome. Okay. Wow. Okay, let's do that again. Okay. Sure. Let's do that again. So that thing was so negatively charged. So as I said, it wants to get away from itself. Given the opportunity, it'll hop off, which is pretty sweet. So it's a suction cup. So if that suction eventually goes away, maybe it'll happen again. It wants to get away enough that it'll actually leap off. And so we played with stuff before that we saw stuff leaping off of there. So given the opportunity, it'll fight gravity and go away. So Yeah, so what's going on is on that dome, you hear the occasional pop. And actually, you can watch the pom-pom. Every time it pops, the pom-pom drops. And so you hear the pop, and then you see the pom-pom drop a little bit, because that pop is actually discharging into the air. So there's a build-up, 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 lots of electrons, lots of electrons. They really hate each other. They want to get away. Eventually, the field is strong enough to ionize the air. And we talked about last class, what's literally happening is the outer electrons on the air molecules are being yanked off. The field is strong enough that it pulls on the protons, pushes on the electrons, and it can yank electrons off the air molecule. I now get a conductive path in the air, and I get a spark, and I hear the resulting shock wave. That's little baby thunder. And every time I get that discharge, there's less field, and I get the pom-pom dropping. Now, what's cool is I am connected to ground. I'm not charged. That thing's supercharged. So it would like to discharge to me. And so you can hear it. And it's doing the same thing. So every time it pops to me, now if I turn the lights off, you might even be able to see it. Let's try it. Is that visible? Yes? Maybe? A little bit? Right over here. Oh, there's one. So, okay. So if I use a fist, if I use a closed fist, I'm trying to make my hand as smooth and round as possible. So it'll build up a lot of charge before it discharges to my hand. If I open my hand, it'll go more frequently. I can get closer. I can do a little tiny spark like that. So kind of the radius that I'm presenting to it is going to determine how much charge builds up than how big the spark is. Oh, okay. Do that one more time. Okay. So I can get it to spark to me, and it'll build up enough charge, Yeah, no, it kind of doesn't want to. There it goes. Okay. So I can build up enough charge, and then it'll discharge to me. Oh, there is a... So hopefully we're seeing that. Okay, there's a good one. Okay, so we can see it. That's lightning. The only difference between that... Jeez, okay, I'm gonna leave it off for a second. The only difference between that and the big scary stuff in the sky is just the amount of charge. It's the exact same stuff. It's a charge separation by friction, by rubbing, and then a discharge through ionized air. It's the same stuff. And then the one thing I wanted to show you before we stop messing with this thing is, okay, so I got that nice and charged up, and you can watch it discharge to me occasionally. So you can see it discharge to me occasionally. Or if I present it with something really sharp, you'll see no discharge. You won't see it. Because this is so sharp, I just get a nice little stream of electrons jumping over here without the big spark. So it doesn't have to build up as much. Something big and round like this versus a fist, it has to build up quite a bit before it'll jump. And you get a pretty loud spark and a pretty big discharge. But something nice and pointy like this piece of coat hanger, I can just discharge it very rapidly. And the amount of field that has to build up is tiny. And I can just sit and keep this thing discharged like that. And then I can go away and let it charge up. And then I can... Okay. All right. Let's turn that guy off. That's probably enough of that. Okay. One last one. Okay. So back to lightning. Lightning is the same process. So up in the sky, I've got moving stuff. So in there, I've got a moving belt. In the wintertime, you've got moving people across carpet, and you get shocks. It's also the same thing. It's electrification by rubbing. And up in the clouds, you just get that on a ridiculously huge scale. And so I've got moving particles in a thunderstorm that are getting charged, and it's usually the negative charges that end up on the bottom. Yeah. Yeah, so that's a really good question. So the reason you get shocked in the wintertime is because as you go around your day, summer, winter, it doesn't matter, as you go about your day, you're touching other things that probably are not exactly at the same place in the triboelectric series as you. You're getting charged all the time. And you're building up a little bit of field all the time. But in humid air, the discharge can happen really easily. So if there's humidity in there, water's a very good conductor. So if there's humidity in the air, as I'm going about my day, I'm never going to build up much charge before it discharges to the air. So I can build up a lot of charge. And so you saw that this thing discharged the air. You're doing that all day long. You are getting little bits of charge, and you're neutralizing that charge pretty quickly in the air, and humidity helps. And so if you want, but in the wintertime, there's less humidity in the air, you can build up a pretty decent charge before you go touch a doorknob or something and realize just how charged you were walking around, and you get zapped because you had a pretty solid charge. And by the way, if you ever see a spark, hopefully somebody sometime in your life you've taken off a blanket or a sweater, or you've just touched a person or a doorknob and seen a spark. If you see a spark, that means you were up in the neighborhood of 10, 20,000 volts. So you're walking around going to class with 20,000 volts of potential, voltage on you. That's kind of nuts. That's a good question. Yeah. Bad for a body? That's a great question. And okay, so Caitlin asked, why is this getting shocked bad for you? Like, why would you not want to get shocked? Because it's kind of fun up here. Today we're going to hopefully talk a little bit about circuits, and one of the circuits I wasn't going to talk about, but it's an important one, is you. And I think it might have been Ampere, the guy that, so we named current after amps, or we named current amps. We say, that circuit drew 20 amps. And amps is named after a guy named Ampere. I think it was Ampere, if I remember right, that took dead frogs and shocked them and made them hop. And just to learn how, it's not gross. You were the one telling me about you like dissecting like cat eyes or something. Sheep eyes? Okay. So when we were talking about eyeballs. Anyway, so so a pretty important electrical circuit, electrical system is you. And so hopefully you know your brain runs on electricity. Your body runs on electricity. So pretty much electrical impulses and electrical signals that's how you work. And so all day long, my thinking, my synapses are voltage differences that make my thinking happen. And when I decide to walk or pick something up or just stay upright, that is electrical impulses that are causing my muscles to contract, including an important one, my heart. And so my heart is getting electrical impulses that tell it to contract all day long, and you can really mess that system up by sending it too much voltage. And so, by the way, I should maybe just, I haven't had to say this much this year, this whole don't try this at home. The fact that we're playing with electricity up here, that could potentially be deadly. So don't get too comfortable with the idea that, hey, look, I got hit by lightning. That's kind of fun. This is high voltage. This is maybe 300,000 or 400,000 volts. Very, very low current. And today we'll talk about the difference between, hopefully today we'll talk about the difference between voltage and current. The current is literally the number of electrons. And so as electrons flow through my body, and so when they jumped to me, they probably went through my whole body to ground, into the floor. The number of electrons was small, and so the electrons actually carry the energy, and there just was not a lot of energy. But I could take a very small voltage and apply it to the wrong place and stop a heart or cause your brain to freak out. And so particularly dangerous is what happens sometimes, like in industrial situations. Someone will grab something that's high voltage, and their hand is at high voltage, their feet are at ground. Their hand is at high voltage, their feet are at ground. The high voltage current wants to go to ground, and a lot of important organs are in that path. And so a lot of current will flow through those important organs. And then the bad thing that sometimes happens is you touch it, your muscles fire by electrical signals, your hand clenches, and you can't let go because your brain is saying stop doing that, but the electricity is telling it to clench. And there's a lot of, sometimes that can be the end, is just you can't let go, and that's bad. So anyway, your heart, it's usually your heart that is the thing you don't want to send errant electrical impulses to. And it doesn't take much. So that's why touching something with this hand, touching something with this hand is really bad, is because right between this hand and this hand is my heart, and so that path, it doesn't take much. It takes like something in the milliamp region to stop a heart. Yeah. Okay. So don't do that. Because I'll probably tell you some other things today that maybe encourage you to go plug yourself into a light socket, and don't do that. Yes? That's a good question. How much is in a defibrillator? Yeah, we might talk about capacitance today. A defibrillator is a little bit like a taser or a camera flash. It can be actually very low voltage, but a lot of current. It's actually the opposite of this. Yeah, that's maybe a good way to think of it. This, high voltage, low current, pretty safe. Defibrillator, low voltage, high current, not so safe. In fact, a taser sometimes runs off a 9-volt battery. And so what's the difference between, you can lick a 9-volt battery, but then a taser will knock you out. The difference is the taser has sat there over several minutes and accumulated charge and then just gone, bah, dumped them all to you in one quick jolt. Speaking of quick jolts, let's finish up. Lightning. I think we talked maybe enough last class about just the physics that we need to know about lightning. So you get this charge separation. You get a bunch of electrons at the bottom that really want to go to ground. That's kind of the definition of electric charge. It really wants to get to ground. And it'll find a route to do that. The way it does it is usually pretty cool. By the way, this video I didn't mention in the last class. I think this video is something like 7 microseconds. It's a very, very short amount of time. It's hard to see in real life, but this is what's going on. And so you get this negative charge at the bottom of the cloud really wants to get to ground. How the altitude between where the charge is and the ground is too much. It's not going to just go bam. It's not going to jump. So lightning is not a spark that just goes from cloud to ground. What lightning does is it ionizes the air in a vicinity, usually like a foot or two of air, and goes through that. And then there's a charge accumulation down there, and then it goes to that, and there's a charge accumulation. And so you can see that the lightning is going in these steps, and it doesn't even know where ground is. But it just sort of randomly, it eventually will find ground, and once it finds ground, it now has a conductive path of plasma, of ionized air, and then there's a rapid discharge, a very rapid charge, discharge to ground, and then they all light up. Yeah, and that's in the region of, gazillions of volts and gazillions of amps, so definitely bad for you. Two other things I want to mention before we move on to electricity. One is a lightning rod is very similar to what I was doing up here. What I was doing up here, was a couple things actually that's kind of neat. This thing, I'm connected to ground. This is very sharp and pointy. So when I subject this to a high electric field, I can probably ionize the air on the tip of this. That's probably what was part of what was happening up here. So when I took this coat hanger up close to the pom-pom, this thing, because it's so pointy, probably ionized the air right at the tip. That ionized air did kind of the opposite of lightning. That ionized air consists of air that the electron's been ripped off of. Now I've got free-floating electrons and positive air ions. And those positive air ions will actually flow to the pom-pom and neutralize it. That's some of what you saw happening. In fact, maybe even a majority of what I saw happening was me sending positive air ions. So those are very negatively charged. All those are running away from each other because they're negatively charged. I can send positive air ions like that and send a flow of positive air ions like that and neutralize it. And that's probably a good reason why that's happening. Now, that's not quite what's going on in a lightning rod. A lightning rod sometimes will do that, but mainly what the lightning rod is doing is just giving the lightning a route to ground. And so what lightning does, and we're going to talk more about electricity today, and all electricity does this, it just wants to get to ground. It'll take every and any path it can to get to ground. And so if you are in the way from lightning to ground, it'll go through you. If a tree or whatever is between that very high electric charge and ground, it'll take that path. A lightning rod just says, hey, look, I'm made of big, fat, solid metal. Why don't you take me? And so the lightning will actually flow through that, and at least a good chunk of the current will flow through the lightning, because the lightning rod is always attached to something that's in the ground. Maybe that part's not always obvious. So when you see a lightning rod on top of a house, it's not, it's not a house going, hey, I would love to get hit by lightning. It's that house saying, I don't want to get hit by lightning. And so what I'm going to do is I'm going to give the lightning a path to ground. So that lightning rod is always attached to a big fat wire, and that big fat wire is in a big stake in the ground. And so when lightning wants to get to ground, it'll take that route, or at least most of it will take that route, sparing your house or whatever else you might put lightning rods on. See them on statues sometimes. Yep. Oh, that's a good question. What happens to the charge when it gets to the ground? The Earth is so big, you can dump a ton of current into the Earth, and it's kind of neutralized. I mean, it's just, and then also the way that the charge even got up there in the first place was probably a charge coming from water, which came off of the Earth. So it's our whole planet is pretty much a closed system, but the Earth is just so huge. I'm trying to think if I've ever seen. Now sometimes a lightning strike will hit the Earth, and if it hits the beach, sometimes you'll see glass. So it'll affect the ground. I mean, it'll kill the fish that it hit in the water it hit, or it'll turn the ground into glass in its vicinity, but that's about it. It'll just in the very small area. Yeah, that's a good question. Okay, let's do. Let's see, we talked about lightning rods. Yeah, let's do an eye clicker. Oh. Okay, so here's our eye clicker number 1 of the day. If you've ever seen a squirrel or a bird on a power line and wondered why is that guy not getting cooked, that's the question of the day. Oh, I got to turn eye clicker on. The line is insulated. Go eye clicker. The line is insulated, that's why. Or B, birds and squirrels are not very conductive, and so the electricity doesn't go anywhere. C, they're fine as long as they don't touch both high voltage and ground. Or birds and squirrels have just learned to live amongst humans, and they don't touch the high voltage part. They only touch the ground line. All right, 20 more seconds. Four more seconds. Okay. This goes into the category of don't try this at home. You actually could yourself go hang from one of those wires and you'd be fine as long as your feet were very far from the ground. And it has nothing to do with the insulation. You can actually grab those wires if they're bare. You just don't want to grab the high voltage one and be anywhere near something grounded. That'll get you a jolt. And again, this also goes in the category of things not to look up on YouTube, but yeah, if they were to touch the high voltage and the ground, then they'd be in trouble. But as long as you're only touching one, you're fine. Here's the analogy I sometimes use: is that what we're going to start talking a little bit more about today is voltage is a measure of it's a measure of potential energy, basically. We'll get into the details of that. It's basically a measure of potential energy. And so if I ever see a sign that says danger high voltage, so wherever you might see that as, I think down in the basement of the physics building, you'll see a sign that says danger high voltage. Maybe the transformer at the physics building has 20,000 volts. It'll say danger high voltage. That's a sort of the equivalent of just being at the top of a skyscraper and seeing a sign that says danger high. There's so much talking in the back. But it's pretty much the equivalent of just seeing a sign that says danger, you're high. Voltage is a measure of potential energy. So if you're at the top of a tall building, you have the potential, and another word for voltage is potential, by the way. when you're at the top of a tall building, you have the potential to fall off the building and get hurt. And the higher the building, the more potential. But if you don't take advantage of gravity doesn't take advantage of the fact that you're really high up, you're safe. So being at the top of a tall building is usually pretty safe. High voltage, not to get you too comfortable with voltage, but high voltage is the same thing. It's safe as long as there's no route to ground. And so a tall building is safe as long as there's no route to ground. And a high voltage is safe as long as there's no route to ground. And in fact, the analogy continues in that if you're at the top of a high building, there is a safe way to get to ground, and that's to go slowly. And if you have high voltage, there's a safe way to get to ground. That's slowly. So you could actually discharge tens of thousands of volts through you as long as it happens slowly. In other words, there wasn't a lot of current. And that's what's happening here with the Van de Graaff machine. I've got maybe a couple 100,000 volts on that thing, but it's not a lot of current. And so I guess, yeah, I can't think of the equivalent for a building, but yeah. So high voltages is very similar to just being on the top of a high building. Yes, there's some risk, but just the voltage itself is not dangerous. It's when it gets lowered rapidly, I guess I should say. Okay, so we're going to talk about power distribution. I do want to talk about one more thing I just remembered that came up last class. Question in the back. That's a very good point, and I think I understand what you're saying, and it's true. Actually, if a bird were to grab, or you were to grab, a high voltage line with both hands, you may have heard that electricity wants to take the path of least resistance to get to ground. The path of least resistance isn't the wire. The path of least resistance is the wire and the bird. And so a portion of the electricity would go through the bird. Yeah, that's a good point. So if you were to go up to one of those high voltage lines and grab both hands on the line, some current would run through you. So there's current going through the wire. That's why there's wires up, and that's why we have power lines, because it's going to somebody's house to power their internet or whatever. So if you were to do this, the electricity wants to get from here to here. And yeah, if the bird were a superconductor, it would go through the bird. Yeah. So yeah, their lack of conductivity is a factor. Now, if the bird were made of wire, like just metal wire, they would have to be as conductive as the wire that they're grabbing on. Yeah. But humans are pretty conductive. I mean, we're basically bags of salt water, but our skin isn't great conductor, so you could probably go grab that, and a tiny bit of current will go through you, but most of it will go through the metal wire. That's a really good observation. Yeah. C. The answer is C. Yeah. Yeah. Question about you should get out. They can make you get out of the pool in a lightning storm. Let's see. Yeah, you don't want to. I think so. The reason you get out of the pool in a lightning storm mainly is you're exposed more than you're in a pool of water. I mean, water's a good ground, but so is ground. So I think if lightning were to hit next to you in the pool, you wouldn't want to be you'd want to dive down if anything. I mean, it could go through you. Once it's there, it's gonna dissipate out of not too far. But I just wouldn't want to be. I wouldn't want to be. Yeah, pools are nice and flat. So if you're above the pool, you're a good route to ground, and you're in the pool, which is a nice ground. So yeah, so if you don't want to get hit by lightning, you don't want to be the best route to ground. Being the tallest in the vicinity is a pretty good indicator. It's not always. You could, if you're next to someone that's twice as tall as you, you could probably both get hit. It's not, lightning's not that observant, but yeah, you don't want to be exposed. Yes, another question. Okay, yeah. So that bird is not charged up. They're at high voltage, And so, yeah, I'm glad these questions are coming up. That bird, if that bird is touching the bare wire, that bird is at high voltage, which is the equivalent of being at the top of a tall building. And when that bird then steps off of the high voltage line or flies away, they lower their voltage, but it's similar to just, it's similar to just taking the escalator down, taking the elevator down. There's no current that needs to flow through them. So here's what you don't want to do. What you don't want is to be in the path from high voltage to ground. And so as that bird takes off, they're just no longer at high voltage. The current, they never were like charged up or anything. Yeah. Okay. One other thing that came up last class, and then we'll get on to a little bit more to talk about circuits, is why the other iClicker from last class was why you're safe in a car. And I don't think we had enough time to explain it. And it has nothing to do with the tires. It has to do with the fact that you're inside a conductive cage. And being inside a conductive cage has a couple advantages. One, again, you just don't want to be the route to ground for the lightning. So when you're sitting inside a conductive cage, the lightning's going to hit the top of your car. Your car is made of metal, and it's going to zip around and go to the floor, go into the ground. So being inside a conductive cage is you're not a good path to ground. So when you're walking outside, you are a pretty good path to ground. You get inside a car, you now are inside something that's a way better conductor than you, and the lightning is probably going to take that route to ground. I think there's photos on the internet where you've seen lightning has gone through airplanes, where the lightning hits the airplane's flying through the thunderstorm, lightning hits the top of the airplane, keeps going, and everybody inside sometimes is fine. Sometimes it fries some electronics, not fine. But so that's one reason. You're inside a path to ground. Another reason you're safe is you're inside what's called a Faraday cage. This is 106.1 The Corner. I don't recognize that song. So what's happening when I turn that radio on, as we've talked about, wherever 106.1 has their antenna, there's a big antenna somewhere in Charlottesville blasting out electromagnetic radiation that is traveling in waves through space, through the walls of this classroom, and hitting the antenna inside that radio. Pretty cool that they can do that. So they oscillate the electrons in their antenna at 106.1 million times per second. That creates electromagnetic waves that fly through the physics building, get to that radio, and it is able to pick up a signal and play whatever that is. Now, all I have to do is surround this radio with a conductive cage like this. So right now, the radio waves are still scooting in through the bottom. But then as soon as I close the cage, and they can't skip through the bottom, I can probably get them through like that. Inside that cage, hopefully you can see them. You guys can hear that from where you are? Okay. Anyway, yeah, the radio waves cannot get in there. And this is often called a Faraday cage. And your car can serve as a Faraday cage to keep you safe in the lightning storm. And what's going on is that inside a Faraday cage, there exists no electric field. And if there's no electric field, there's nothing to push or pull on your electrons, and you're probably going to be safe. And the reason there's no electric field is just like the radio wave that was coming in here, the electromagnetic wave coming from 106.1 The Corner, once it got here, this cage is conductive. In other words, it's made of mobile electrons. Another definition of an electromagnetic wave, or the electric part of the electromagnetic wave, is an oscillating electric field. As we've talked about, fields push on charged particles like electrons. So as soon as this thing gets hit by an electromagnetic wave or any electric field, the electrons in here will get out of the way or reorganize until they cancel out that electric field. So the electrons in this cage actually moved and reorient themselves. They move and reorient themselves to cancel out the electric field. And on the inside, there's no electric field. In fact, one thing I was going to try, I could probably do that with this guy. I can do a similar, I was hoping, let's see if I can get this guy close enough. If I can get this guy close enough that he's getting charged, a little bit. So you can see that those streamers are now subjected to an electric field, and they're kind of being pushed to the right a little bit. Can we see that? Yeah. And then if I put them inside a cage, that's not a very, yeah, let's see that. If I put them inside a cage, it's uniform. They're all charged. I should discharge it. So they're slightly charged, so it's uniform. But then when I take it out, you can see the electric field exists here. But when I put the cage down, the electric field doesn't exist right there. Not the best example. I just thought of that. Thought we'd try it. Okay. So yeah, that's a Faraday cage, and it's basically it cancels out the electric field, and that's another reason you're safe inside the car. Okay. We have 8 minutes left. Let's start talking about electricity. And so, like I said, what I'd really like to do is start talking about not just static electricity, but electricity that gets moving. And here's a pretty good reason in a class called How Things Work to start talking about electricity. Your brain and your heart runs on electricity. Your phone, the lights in this room, your car runs on electricity. Not just Teslas, all cars run on electricity. Your laptop, pretty much everything runs on electricity. Your refrigerator, your microwave, it's pretty much what makes modern life possible. It's what makes your iClicker work. It makes everything we do, pretty much everything we do in modern life runs on this thing called electricity. Not just static electricity, electrons just hanging out, but the flow of electricity. So I'd love for us to start understanding that a little bit. Here's my simplest circuit. And what we've kind of already talked a little bit about that I want to formalize a little bit is here's how you get electricity to flow. You don't just get high voltage. So if I were to walk around with a battery, that battery is not running any current. So if I just had a battery is a source of voltage. Maybe we need to know that. So my battery is a source of voltage. That's not electricity. I can hook up my battery to a wire. I still don't have electricity. The way when I have electricity is when I give the voltage in the battery a route to ground. When you talk about a battery, the ground is the other terminal, usually labeled negative. So when I pick up a battery, like a 9-volt battery, and the 9-volt battery's got 2 terminals, one's labeled positive, one's labeled negative. All that means is that the positive terminal is 9 volts above ground. And that ground is super relative, by the way. And kind of like way back when we were talking about gravitational potential energy, I can call anything 0, I can call anything ground, I can call this table ground. And there's things above this table, I'll call those have positive energy. There's things below this table that have negative, exact same situation. So the power company doesn't send me just, so the power, wherever the circuits are, the power company doesn't just send me 120 volts. That doesn't mean anything. I can't just say, hey, I just sent you 120 volts. What the power company has to do is send me 120 volts and ground. And their job is to send me 2 wires separated by 120 volts. That's why the plug has at least 2 holes. And when you plug something in, you need 2 prongs because I need a voltage difference to drive current. So one of those prongs is 120, the other one's 0, but that's relative. And when I pick up a battery, it's the same deal. All the battery, when I buy a battery, most AA's are a volt and a half, 1.5 volts. So when I buy a AA battery, all that means is there's a chemical situation in there that has raised one terminal 1.5 volts above the other. So in order to get current to flow, I need just 2 things, I guess. I need a voltage difference. In the AA battery, it's 1.5 volts. And I need a route to ground. That's all I need. And then I get current. In this picture, there's 3 things. There's a voltage source, that's my battery. There's a route to ground, that's the wires. And there's a source of resistance, that's the light bulb. And let's see, in this class, yeah, let's talk about the relationship between those 3 things. This is our one relationship for the next week probably that we need to know. It's often called Ohm's law. A guy named Ohm figured this out. And it's just the relationship between your voltage, your current, and your resistance. And it's pretty straightforward, V equals IR. So I've rearranged it below there, I equals V over R. It's usually the way I think of it. So the current, I don't remember why we labeled I, but it's I. The current I is determined by 2 things. How much voltage you have and how much resistance you have. So that's why, let's see, I can plug myself into a decent amount of voltage because I have a very high resistance. Last time I measured it was like 22,000 ohms, or 220,000 ohms, I think, last time I measured it. So I can plug my hands into 12 volts, and I'm not going to get a lot of current because between my hands, there's about 200,000 ohms of resistance. plug 12 volts into 1 ohm of resistance, you're going to get 12 amps of current. So there's the relationship. You've got your voltage source. Another word for voltage source, by the way, sometimes it's referred to as electromotive force. And what that means is voltage is that thing that wants to get current going. Again, back to my analogy of the tall building. Tall buildings are things that want to get mass to ground. So if I want to get a circuit going, I can lift a bunch of things above ground and I can let it go. And a battery is the same thing. It's taking a bunch of things above ground, but then if I walk around with a battery in my pocket or a charged cell phone or something like that, all I've got is just a bunch of electrons above ground. It's when I let them go to ground, that's called current, and that's what makes life possible. So when I turn my phone on, so my phone right now is not doing much. It's on, so it's probably talking to the cell tower. But right now, there's a voltage source in here. If you ever take a phone apart, this phone is like 80% battery. Because we want to be able to store a lot of charge, and they've had to make everything else super small. So when I turn right now, when I turn my phone, like when I turn the screen on, oh, and by the way, with 2 minutes left, this is maybe the last lesson that I have to tell you, and that is everything happening in this phone, what's happening in this phone is extremely complex. It's exceedingly complex. There's, like we've talked about this before, there's a Bluetooth antenna, and there's a Wi-Fi antenna, and there's a cell antenna, and there's a memory, and there's a computation, and there's a video card, and all that complexity is one thing, and it's electrons falling to ground. That's it. Everything that makes this modern life and this phone possible, it's electrons falling to ground. So when I turn the phone on and the screen lights up, some electrons went to ground. When I make a phone call, the antenna is being excited by some electrons falling to ground. When I hit save photo, and that saves it in the actual memory of this thing, a bunch of electrons went to ground and flipped some circuits, and now I've saved it. Everything going on in modern life, including your own thinking and your own muscle contractions, is electrons falling to ground. And maybe that's a good place to stop. Are there any questions? Have a good weekend.